in the last class, we were discussing about that shared memory SIMD, shared memory model sorting algorithms, and just we completed the merging technique, and right on CREW model and on EREW model. Now first let us discuss the sorting on CRCW model. And the sorting technique is enumeration sorting technique. And you remember that enumeration sort is nothing but that every element is compared with every other element, and he keeps the rank and then he moves the data into that position. So here also same thing. For suppose I have n processors and n elements to be sorted for I equals to 1 to n, do in parallel. PI compares AI with AJ if AI is greater than AJ and or AI equals to AJ and I is greater than J, PI writes 1 to CI, CI is the counter, else PI writes 0 to CI. PI writes PI 2 1 plus CI. So this is your algorithm that for I equals to 1 to n processors are activated, and this is an iteration for n because every element has to be compared with every other element. A PI compares with AI with AJ, and then if AI is greater than AJ or both of them are equal but J has occurred prior to I, then PI writes 1 to CI because, right, else PI writes 0 to CI. So the CI gives you the count where to move, where to move, right, and PI writes AI to 1 plus CI, right, and this writes 1 means add 1 to CI, basically add 1 to CI. So this is order n time complexity, and cost is order n square, which is matching with your enumeration sorting algorithm. But obviously it is not cost optimal because enumeration sort itself is not a cost optimization. It doesn't give you n log n time complexity. Agree? Now, this algorithm also can be thought that way, that suppose I have n square process, then also you can use it. Only the Pi writes 1 to Ci. Here you will be writing for j equals to 1 to n, do in parallel, and Pi writes 1 to Ci, right? This is actually, instead of that concurrent write is coming, that several process wants to write into Ci. So basically that procedure that I mentioned, that while in order to handle the concurrent write, there are several modules, several ways you can think. One is that you assume that minimum of the processor index should be allowed to write, or some of the values can be allowed. So here, sum of ones will be written into Ci, right? So we assume that that will take constant amount of time. So this whole algorithm will take constant amount of time to sort n elements using n square processor. The cost is becoming order n square. Time becomes order 1 in that case. Is it okay? Now the next model is CREW model. Here you have n processors, n elements, and n processors. And these n elements are in the sequence S. Now initially you divide S into n groups, each of size n by n. Each processor so you have basically n groups, each group is having n by n elements, and now say let us assume that S1, S2, S3, Sn, S1, S2, Sn by n, these are the groups, right? And Pi is attached to Si, so each processor sorts the elements of Si, right, attached to him, using any sorting algorithm, maybe quick sort, and you assume Si1 is your S1 Si, and Pi1 is the processor Pi. That is, the set of processors is defined by Pi1. Now what happens, that you have several sorted subsequences, and you know now CREW merging algorithms, right? You know CREW merging algorithm that we discussed in the previous class. So use 2 processor to merge these two, 2 processor to merge these two, 2 processor to merge these two. Next time use 4 processor to merge this, 4 processor to merge this. Next is 8 processor to merge this, and so on. Right? That algorithm we have discussed. So same idea we'll be using here. This UE and V are the U is that number of iterations that at ith step how many process to be handled, that parameter, that u is initially 1. This is why I want to write, that is the first stage, u is giving the stage number, and v is that number of processor employed, or number of iterations you have to do, that is, that you need to do the log n iterations, right? First, second, third, and log n iterations. So v will take care of that one. So while v is greater than 1, so you have to merge it. So you define the number of processors you are going to employ is pi 2u, or pi 2u is equals to pi u and pi plus, I don't know whether I am writing correctly or not. Shall I write? No, it should be 2i and 2i minus 1. Processor here you have to write for I equals to 1 to n doing parallel. For I equals to 1 to n doing parallel, this n processor you are employing, so 2i this is 2u or u plus 1. This will be u plus 1. Is P2i minus 1, that is I equals to 1, so P1 and P2, whatever set is there, that is you are adding here, right? So that many processors you will be employing to call CREW merge. Which routines? It is S 2i minus 1 u S2i u GBU SI u plus 1. Right? So you are merging these two sequences, stores in the run data SI u plus 1. And then the simple thing, you will be u is increased by 1 and v is decreased by, size is reduced, v by 2. The only thing is that here I am assuming that n is always divisible by 2. N is always divisible by 2, right? So here I am assuming that you can always pair in 2, 2, 2, 2. But if it is not divisible by 2, what happens? You just bring down here without merging anything. Agreed? So if it is not divisible by 2, just you have to write one line that this is as it is, and instead of merging, just this will be transmitted to this. Nothing else. And u is increased by 1, v is decreased by 2. So this is your algorithm. Agreed? Any confusion at this stage, please let me know.
Incrementing u and v, is this in the for loop?
Pardon me?
This is outside the for loop.
Which one?
Incrementing u and
Yes. This for loop is activating all the processors. This all the processors you are activating, nothing more than that. Right? This is not you are iterating. You want to tell that all this processor you activate to now, once you make all the processor activated, some processor will be used for merging these two sequences, some process will be used to merge this, some process will be used to merge these two sequence and so on. Which are those processes to define that? We have used this one. Which are the subsequents to be merged? To define that, we have defined this one, and the resultant will be here. And U will be increased by stage, next stage. So that's why U is U plus plus. And size will be that it is half, right? So number of clusters will be half. So that's why it is V by 2. Is it okay? Now, if I have to compute the time complexity for this, for step 1, how much time you need? How much time? Capital N. How can you do that in capital N? Huh?
N by N multiply log N by N.
Yes. So, step 1 takes this much time because you are using any sorting technique, and the first one, division, doesn't take much time because it is logically only your, because the concurrent read is allowed, so there is no problem. Now in the step 2, you observe there is a while loop, and every time you are halving it, right? So this will be iterated log n times. Agreed? Now at the ith time, what is the time complexity you have to find out, or at the vth time. Now you go back to your lecture note, you see how much time you need for merging the two sequence. What is the time? You see the merging two sequence, we discussed this one.
So the merging is outside the for loop.
Merging is?
Outside the for loop.
Where is the for loop you are looking every time looking for?
I equal to 1 to 1 do in parallel.
What do you mean by this for loop? First you tell me, what do you mean by this for loop?
For all the n processors, we are doing this.
We activate, but this is not that iterating anything, right? This is to tell you that this many process you are activating. So
Yes.
this I is dependent on this. So how can you tell that this is outside the for loop? What is the time complexity? You remember? If you have n and n, something there, right? What is that time complexity? CREW model. Not there? N by n plus don't get, eh? Plus log n by n plus log n. Did you get that? That algorithm you got it or not? CREW merge algorithm have you got in your lecture note material? Yes or no? Yes. Victor did not get it. Is not there? Binary search, finding the j smallest I less than equals to j. We wrote several things in that. It is based on binary search. No? It is not there? Before median pair.
28.
Huh? So what is the time complexity we obtain? Order n by n log n. Not there? Huh? Max of RNS. Then
Log S
log R. Log. Then if R equals to S equals to n, so it will become
N log N.
Is it okay?
Plus
N log n is coming later for finding the cost and something like that.
Yes, that is the cost.
So this is the thing I am writing. This is small n because this is the size of the elements in the sequence. This is the number of processors you have employed. This is the number of processors you have employed. This is the size of the sequence. So n by n plus order log n. N is your n by v by 2. Yes. So this can be written as order log n into order, this is n by n plus log n, right? So which I can write order n by n log n plus log n log n. So the Tn is order n by n log n plus log n log n, right? Because this is n by n and this is larger. If I write this is log n, then this gets cancelled, right? This gets cancelled, right? Log n minus log n will be coming, plus log n will be coming, so log n plus this. Agreed or not? So cost becomes order n log n plus n times log n log n. Tell me. Here is a lot of problem, I think.
Where will the number of processors log n capital Tn?
Tn is equals to n by n log n, and you have the step 1 n by n log n by n. So this capital N will become minus n by n log n, and this is plus, so this gets cancelled. Right? Now this becomes cost optimal if capital N log n is less than equals to order n. That is, I can write n is less than equals to O n by log n. Right? Because capital N is smaller than small n. So this becomes cost optimal if now if I use this one for EREW model, you have to pay extra money for this broadcasting things, right? Because this is concurrent read, I thought. Now the broadcasting will take another log capital N factor, because capital N elements will be there, so you have to broadcast it. Same thing happened here also, because this is, you are doing the binary search, if you remember, right? So that binary search will not be allowed. So here also you need log n factor. So log capital N factor will be added into that. And if you add this one, then it will not, no longer it will give you the cost optimal algorithms. Right? Now, what happens if I replace CREW model by EREW merge algorithms? Right? We discussed EREW model by median pair elements, if you remember. Right? In that case, what is the time complexity is coming for that? Can you find out? In that case, the step 1 will take order n by n log n by n. Step 2 takes, obviously this iteration you cannot get rid of it. Now you tell me EREW model here instead of CREW model, EREW merge. What is the time complexity? My record tells it is order n by n plus order log n log n. Is that thing? So this gives you order n by n log n plus order log n log square n. So if I add these two, I get the Tn is order n by n log n plus log n log square n. And the cost becomes so this has to be, in order to make it cost optimal, this has to be n log n. This has to be n log n. That is n log square n must be equals to order n. Right? Which you can write n must be less than equals to order n by log square n. In case of CREW model, it is cost optimal when n is less than equals to order n by log n. In case of EREW model, it is cost optimal when n is less than n by log square n. Right? Now the problem, both of them are cost optimal, that's okay, but point is that you know that EREW model, that your size is much less compared to CREW model. So can we think about some alternatives? So in order to see the better algorithm for EREW model, we need to go back little. That is, we are interested to find out finding the kth smallest element, from a sequence of n elements, right? That I think we have discussed this thing earlier also. Kth smallest element. S is having n elements. Let us think about sequential algorithm first, and then we will go for the parallel algorithms, and then we will try to use that one to find out the sorting algorithms for EREW model. Now, in the case of sequential algorithms, if you remember, Bloom's algorithm is that you divide the sequence S, this S, into S by 7 groups. Each group is having 7 elements, right? Now, later on it has been shown that 7 is not the constant. Any constant number of elements, right? Any constant number of elements in each group. Only condition is that you must have the best known or minimum number of comparison based sorting algorithms for those number of elements. Suppose in this sequential case, you divide into n by 7 groups, each is having 7 elements. So in case it is not divisible by 7, then your last subsequence may have some padded 0. And then you sort each group which takes constant number of operations. Then you find out the median of this median elements by recursive process. Suppose this is the median element. This median element is used to divide this whole sequence into the 3 groups. The elements which are smaller than this, elements which are larger than this. Now, if you find that these elements, total number of elements is smaller than this, is more than k, then kth element is lying in this zone. If you find that no, the total number of elements is smaller than k but larger than this part, so it is lying here, that the median element itself is the kth element. Otherwise, your sort zone is reduced to this, right? So, time complexity, it was shown that sorting takes constant amount of time. Finding the median of medians, that is recursively you will be finding. So, recursive call will be there, and after that dividing into the 3 groups, which takes order in times, and then again you are finding that it has been shown that in the worst case that only 1/4 elements will be discarded from your searching zone, so remaining 3.4 elements will be there. So you have the searching size reduced to Tn by 4, and it is a 2-dimensional recursive routine is coming, but ultimately it has been shown that it takes order and time to find the kth element, right? This is the standard Bloom's algorithm, so which obtained in 1973 or something like that. So the same idea can be used for finding the kth element in S. Here we are assuming n elements, number of n elements, number of processor is can be expressed in the form of n to the power 1 minus x. X is lying between 0 and 1. Now, if the number of elements is very less or constant, so what you do in the case of Bloom's algorithm, you directly go to the kth element, you sort it and get the kth element, right? So if the number of elements. If n is small, then just sort sequentially and get the kth element. Else, if it is not small, then only the question of using the parallel processing is coming into the picture. You divide these n elements into capital N groups. Each group is having n to the power x elements. Divide n elements into n groups, each of size n to the power x. Group I, or a group, n groups, let us name it here, S1, S2, Sn. Group Si is attached to Pi. So basically, in corresponding to the sequential algorithms, what we have done here, instead of 7 elements, we are putting n to the power x elements. We are putting n to the power x elements instead of 7 elements, and here you have total number of processors is n to the power 1 minus x. For each processor, you have n to the power x, and sequentially, I want to find out the median of this n to the power x elements. Agree? So, each processor Pi finds median Mi of Si sequentially. Let M is M1 union M2 Now you have got what you got the median of each sequence. You have to find out the median of medians, right? So you can call this PAL select algorithm again. So you call PAL select. You have capital N. You have capital N, and you have to find out n by 2. Right? So you have much more elements, number of processors than the number of processors required in reality. So through that you got, oh, actually I need the return thing, right? I think I put here x. Here also return is x. So I got the n by 2th element, which is x. Now this x is your partitioning element to divide into the 3 groups. Agreed? So Pi step 4, let me write here. Step 4 is PI uses X to divide SI into 3 groups. Li, EI and U, such that Li contains all the elements Ai, where Ai is less than X, EI is containing all the elements X, and UI contains all the elements AI, where AI is greater than X. So that is the thing actually you did in the case of sequential. Same thing we are doing for each processor. Step 5 is nothing but, now you have to find out the globally total number of elements smaller than X, total number of elements equal to X, and total number of elements of UI, because otherwise you will not be able to know that one. So processors are used to find L, where is L is nothing but L1 union L2 union Ln, U, E, U1 union E2 UN and U. Agreed? So now you get L, E and U. So L, you find out the size of L. If you find the size of L is less than K, then you are calling this routine on this. If you find that size of K is sum of these two, then you got already that it is your kth element. Otherwise, you will be getting the kth element from there. That is step 6. Step 6 is, if size of L is less than K, greater than equals to K, then you call PAL select from L. You have total number of processors. You have to find out the kth element, returned is your X. Else, if L plus E is greater than equals to K, then X is the kth element. Else, you call PAL select from U N, and this K minus L minus E, and return is X. Now tell me what is the problem. First, what he did, if the size is small, sequentially you sort it and find the kth element. Otherwise, you divide these n elements into n groups. Each group is of size n to the power x. And group Si is attached to Pi. So sequentially Pi finds the middle element of Si, and this middle element forms M, and then sequentially you call PAL select algorithms, and to get the median of medians, that median element you are using by each processor to divide into the 3 subsets Li, EI and UI. Li contains all the elements smaller than X, EI contains median elements, and UI contains all the elements greater than X. Now you have to combine these Li's, UI's and EI's. So you have combined them using all the processors. And finally, after obtaining that, you have to see that whether the size of L is greater than or K or not. If it is greater than or equals to K, that means kth element is lying in L. So you are calling this one. If it is not, if it is finding that these two are equal greater than this, then kth element is your x. Otherwise, the kth element is lying in u. So u n k minus l minus u e you have taken care because those things are anyway smaller than that and x. Agree? So in order to find out the time complexity, this takes constant time. There is now this is constant. This is also constant time. In the case of CREW model, in the case of EREW model, you have to broadcast. So log, in the case of EREW model, it will come order log n time. This is for EREW model. Now each processor finds the median independently. Size of Sx is order n to the power x. So this will take order n to the power x. This is the same time. If Tn is the time, then what should be the time here? T n to the power 1 minus x, right? Because size is n to the power 1 minus x. Now, Pi is dividing his subsequence into Li, Ei and Ui. So this will take order n to the power x. Because you have only n to the power x and this you will be moving here and there. Agreed? Now tell me about this one. How can you do it?
Taking count of individual LIs and
Yes. So what you have to do, you have to find out the total number of elements Li, because once you are computing this one, you can find out the number of Li's, right? So if I know a priori the number of Li's, number of L1, number of L2, number of L3, so this can be done through cumulative sum. So what should be the starting address of the next processor? Starting address of the processor, so which takes log n time. So log n, agreed or not? Which takes log n time, and then you will be moving the data, right? Each processor will be moving the data of n to the power x only. So here this one will take order log n to the power 1 minus x, that is log n, plus n to the power x. That many data movement in the worst case you will be moving. Yes? So you got L, and then this is known to you. This size will be T, size was 3 by 4n. Because that is the worst case, you can discard only 1/4 of the element from your searching zone. So remaining will be in your size. So the time complexity becomes Tn is equals to order 1 plus order n to the power x. Okay, here order 1, instead of that you should type log n, say log n to the power, order log n to the power 1 minus x plus order n to the power x plus t n to the power 1 minus x plus order n to the power x plus order log n to the power 1 minus x plus order n to the power x plus t by 4n. So these are, this one, they are smaller than this n to the power x. So this is the primary one. So this will become order n to the power x. As we did in the case of sequential algorithm, same sequential algorithm technique here. So it becomes order n to the power x. Okay. So the Tn is order n to the power x. So what happens Cn? Cn is order n. Because that was the n to Tn is P is n to the power 1 minus x. So if I multiply it, I get order n, which is cost optimal. Right? So this is true for EREW model also. Because I have considered all the things on EREW. You have n processors or n elements and n to the power 1 minus x processors. X is satisfying this condition. Now, each processor PI finds MI each processor PI finds MI. MI is nothing but I into n by 2 to the power 1 by x, the smallest element of S, where I is 1, 2, 3 up to this. That means basically what we are making, that you have S elements, you are dividing into 2 to the power 1 by x groups. Right? This is your M1, this is your M2, and this may be your M 2 to the power 1 by x minus 1 and n by 2 to the power 1 by x of the element. So that many groups you are making it in such a way that all these elements will be smaller than these elements, all these elements will be smaller than these elements, and so on. Right? And each group is having how many? Each group will have how many elements in that case? Each group of size. What is the group size? Total number of elements is n, and you are making that many, so total group size is this. Except the last one. See, I am finding the first, I am finding n by 2 to the power 1 by x smallest element, 2 times n by 2 to the power, so these are equidistant. These are equidistant. Maybe one element will be in this side, maybe another number, because it may not be exactly divisible, that's why it may come out that one. But 1 or 2 elements plus minus this side will be there. But what happens, you divide these M1s, you can find M's, you can find out. Now once you find out the M's, you can use these M's to find from the S to bring the elements which are smaller than M1s this side, larger than this side, and so on, so that these groups are satisfying the property that all these elements will be smaller than these elements, all these elements will be smaller than this element, and so on. As we did in the case of finding the kth element on EREW model. Agreed? Is it okay? Yes. So this use MIs to divide S into 2 to the power 1 by x groups, each of size n by 2 to the power 1 by x. And these groups can be S1, S2, Sj plus 1, S2j, where j is equals to 2 to the power 1 by x minus 1. Satisfying the property that equal to all elements of Si plus 1 for all I. Now basically you have S1 is a subsequence which contains all the elements smaller than this and so on. So recursively, I will tell why recursively is possible later on. Recursively you employ some processor to do S1, merge, S1 sort S2 and so on. If I can do that, then your problem is solved, right? So these elements if I sort, these elements I sort and so on, then the problem is solved, right? So I can do it for I equals to 1 to n is it n or 2 to the power x? 2 to the power 1 by x. Do in parallel sort Si. J 2 to the power x minus 1. J. Also for I equals to next 2 to the power 1 by x to 2 to the power 2j. 2j is what? Go down here. K is 1 by x, agreed or not? Here it will be minus 1 here. So to for this, I will come to this again. To the power x. Then this is minus 1 plus 1 to this. Do in parallel. Sort Si. See, basically what we are doing this part and then this part. That is the thing I want to do. This part we do sorting for each of them. After completion of this, then we do the sorting on this part. Why it is so? Because I have the less number of processors to employ. Only thing is that can we use it recursively or not? That is the thing yet to be shown, and we have to show that the time complexity. See, this part is simple. For each processor, Pi finds Mi, right? This is finding the kth element. Then use Pi. Use Mi to divide S into these groups. That you did Li, Ui, Ei, and then union of this. So that will be found here. And then these two parts. Now here you observe you are employing, how many sequences are there? S1, S2, S2 to the power 1 by x minus 1. That many sequences you have here. Right? I am merging S1, S2, Sj. So that many sequences you have. And what is the size of each sequence? Huh? N upon 2 to the power 1 upon x. Right? And I am employing for each sequence I am employing that many processors. Because I have total number of processors. Is n, and there are j subsequences. So each subsequence can have n by j processors. Agreed or not? More maximum I can give, not more than that, right? Because total number of processors is capital N, and there are j subsequences. So n by j. N is what? N is n to the power 1 minus x. J is what? 2 to the power 1 by x. Hey, this is minus 1 is not here. This is minus 1 here. This is minus 1. So this is minus 1. So it becomes 1 minus x. So n by 2 to the power 1 by x, 1 minus x. Right? N by j becomes n by 2 to the power 1 minus x to the power 1 minus j.
So can you explain?
Which one?
So this S1 has n upon the enumeration.
See, how many subsequences you have? J subsequences, right? And how many processors you have? Capital N. Because that is the processor total. So what I want to say that recursively I must be able to use it. Recursively I must be able to means given n elements, I should be able to use n to the power 1 minus x processors. Then only you can recursively call this routine. Agreed or not? Now you have j subsequences, and each subsequent size will be n by 2 to the power 1 minus x, 1 by x, and you have total number of processor n. So j subsequence, so you can give at most each processor n by j processors, because total number of processors is capital N. J subsequences, if you give the equal number of processors to each subsequence, then it is n by j processors, which is nothing but n to the power 1 minus x divided by 2 to the power 1 minus x minus 1, which I can write n by 2 to the power 1 minus x to the power 1 minus x. So your total number of elements, suppose it is k, then I can write it is k to the power 1 minus x form. So if you have n, number of processors is n to the power 1 minus x. If you have k, you have the number of processors k to the power 1 minus x. So you can use recursively to sort S1, S2, Sj using that same total number n to the power 1 minus x processor. You have not taken any additional processors. Agreed? If it is the case, after that again same way you can do this one. Right? So finally you will be getting that sorted sequence. So you observe this takes order n to the power x time. This takes order n to the power x times. Agreed or not? Because that we have already done it. So the time complexity Tn becomes order n to the power x plus 2 times T n by 2 to the power 1 by x. because size is reduced to n by 2 to the power x. It's okay? And the solution to this is right? It's okay, yes. If it is the case, then Cn is because number of processes is n to the power 1 minus x, so you get C order n log n. So this is always cost optimal, right? Only what is the constraint on the process n to the power 1 minus x? You must be able to write in this form, right? Which is always you can find out of that it is always less than or equals to n by log n form. So this becomes cost optimal on EREW model even if n is less than or equals to n by log n, which is matching with CREW model. So what are the things we have covered? We have covered all sorting algorithms. We have covered merging algorithms. We have covered finding the kth smallest element, right? Yet to be covered searching kth smallest element, another one I will cover. And then matrix theory and the graph algorithms, right? And combinatorics.